Now we'll be talking about wavefronts. Wavefronts are pretty similar to crests, but they're often used in different contexts to the context in which crest would be used. So when we think about a wave spreading out in, for example, a pond, we can use the idea of wavefront to describe where the wave is. A wavefront is the crest of a wave as the wave spreads out. So in the case of a ripple, the wavefront will be circular and it will spread out in all directions. We can sort of say that this wavefront is the location of the wave when we're analysing how it moves. So it might be straight. Waves on a beach are often seen as being pretty straight, just flat lines moving toward the shore. They might be circular, like in this example, or they could even be spherical, like a sound wave spreading out from a source of sound. So let's apply some of these terms to real-world waves, in particular sound. So the amplitude of a sound wave determines its volume and its intensity, for that matter. The frequency of the wave determines its pitch, so whether it's high or low, right? And the speed of sound depends on the medium through which it travels. And if we know the frequency and we know the speed, then we can use that to calculate things like the wavelength. So in air, which is what we're of course all used to, sound travels at about 340 meters per second. Waves with higher amplitudes always have lower frequencies. Now, what's amplitude a measure of? It's a measure of the total displacement of the particles, right? But frequency is a measure of how quickly the wave is moving through space. So what this means is that whether or not it has a high or low amplitude, it could have a high or a low frequency. So our answer here is going to be false. B. Waves with higher frequencies always have lower periods. Now, what was that equation relating frequencies with periods? F equals 1 on t. So if t is very large, f will be very small. And if t is very small, then f will have to be very large. So in this case, it's true. Remember that the period is how long a wave takes to travel one wavelength, and the frequency is how quickly the wavelengths propagate, or how quickly the wavelengths pass through a particular point in space. So we can see, just from that description, that if we have a high frequency, that is, if a wave is passing through a particular point with many wavefronts per second, then the period, how long each wavefront takes to get through, will be very small. C. Waves with higher periods always have lower wavelengths. Now this is an interesting question. We know that if a wave has a high period, it will take a long time for a wavelength to travel through a particular point. And we know that if something has a low wavelength, then it will be very bunched up and together. But what we don't know is the speed of the wave. If the wave is traveling extremely quickly, then it might have, even if it has a very high wavelength, it might have a very low period. On the other hand, if the wave is traveling very slowly, then it will have a very large period, even if it has a short wavelength. So in this case, we can't really say. And that means that we can't say that they will always have lower wavelengths. Our answer then is false.